Good morning, everyone. Let's begin. Any more submissions for the evaporation homework? Evaporation? All right. I've handed out copies of the notes and the next homework assignment. Does everybody have that, the notes and the assignment? Okay, they're all up here if you came in a little bit late. I think there must be extras somewhere because I printed off 23. Is there another set of notes somewhere? I know that there are because I printed off 23 of them. Well, let me inspect every single row of desks here. Who's got the extra set of notes? Anyone? Oh, you got one? Okay. All right. Well, the infiltration assignment will be due a week from today, and we're going to introduce that. We're also going to go over evaporation pans just to sort of finalize the discussion about evaporation. Looking into the future, on October 30th, we're going to have a recorded class meeting. That's a Thursday. We won't be meeting in class because myself and Dr. Pearson are going down to Clemson for an FE meeting. So that's not on the slide there, but if you want to put it in your calendar, you'll be able to sleep in a little bit later on the 30th of October. All right. So evaporation pans are a way to physically extrapolate how much evapotranspiration there is in a watershed by using a physical model. And so what you're trying to do is you're trying to measure how much water is lost from a small pan like this, or sometimes if they want to know how much evaporation there is from a lake rather than from crops, they may have some sort of a floating little boat system, and you can't see it very clearly, but in the center of this floating boat is just a little pool where they're measuring the water elevation very carefully to find out how much it's dropping over a certain period of time. And the purpose for this is to basically have a physical tie rather than just using strictly equations to predict how much water is going to be lost, and then to link how much water is lost from a pan to how much would be lost through a crop, and likewise how much is lost through this small little wading pool that's out in the middle of the lake to how much would evaporate from the lake itself. And so this actually takes into account all the variations in the sun, the humidity, the wind speed. In your homework assignment, what you had was the solar radiation at 1 hour increments. But during that 1 hour, if they're measuring it at 9 o'clock and 10 o'clock, it might be that for a brief time in between those 2 hourly measurements that it was cloudy. Now, this will take into account all of the variations in real time that actually occur in a spot. So it can be an effective way of measuring evaporation. Yeah, then you're going to get results that are unexpected, right? So they'd normally fence off a pan in the same way that they fence off a weather station, try and keep vandals. And you also have to measure how much rainfall there was, because if the pan suddenly is deeper rather than losing water, if you gained water, you'd have to have some way to explain that. What this table shows is the effect of wind speed and also the effect of where the pan is located on how you correlate the pan evaporation to the actual evapotranspiration that would happen for crops and soil. Because in hydrology, what we're interested in is how much evaporation was there of precipitation that had hit the surface. We're not always only interested in evaporation of liquid water from a free surface of water. So it's not just only ponds that we want to know how much evaporation there was, but we may want to know how the soil moisture decreased. And so what you can see in this figure, first of all, there are different categories of wind speed. And so light, moderate, strong, very strong, they classify the wind speed as one effect. And we know that wind speed has a big impact on the amount of transport, because it is trying to get away the moisture from the surface of the water so that you can have dry air above it, and that gradient drives additional evaporation. Now this next column, upwind fetch of green crop, that's talking about if where you have the pan located in a field. And so if the wind is blowing this way, and this is grass, and then we have our pan located here, the grass itself could be giving off moisture, and so this is water that's being lost. It's coming up from the grass so that when the wind finally gets to the pan, it may be that the air packet that's above the pan, the air is saturated with moisture. Or if it's not fully saturated, it's going to have more moisture in it than it would if, what if the pan, instead of being downwind of, you can see here it's saying up to 1,000 meters of crops, what if the pan was right here? So that now the air that is coming past it is dry air, and it doesn't have green crops that are immediately upwind of it. So if you're trying to say, well, here's our pan and we lost 1 inch per day from the pan, and the question is, how much did you lose for the whole field? You're trying to create a relationship between the pan evaporation and the field evaporation. Well, where the pan is located in the field is going to affect which factor you use. And so this is a table of K values. And in this equation here, on the right side of the screen, it says that you can find the evapotranspiration for the crop by using the pan evaporation. E sub P is the evaporation of the pan. And then the K sub P, the pan coefficient, is this table here. And so what you'll notice is that if you have a lot of upstream upwind fetch of green crop, then the pan coefficient is 0.75. But if you have hardly any upwind fetch of green crop, it's 0.55. So that means the more downwind it is, the greater the relationship between the evaporation of the crops that's in a field and the pan itself. And then the other effect you can see is humidity. And so there's columns here that are taking into account how humid it is. And there's a pan surrounded by short green crop, pan surrounded by dry, bare earth. And so sometimes a pan could be used to estimate what's happening with the field of grass. A golf course may wonder how much moisture they need to put on the golf course because water is very expensive, and especially in places like in the western United States where they have to irrigate, they don't want to put on any more water than is absolutely required to overcome the evapotranspiration. And so having a pan somewhere to actually watch over time how much moisture is being lost by the pan, and then a table like this to tell you how the pan and the grass at the golf course actually relate to each other can be very useful. It can be a way of not having to overwater. We're going to take a look at this by trying out an example where we have wind speed given. This is in northeast Ohio. I don't know why that matters necessarily, northeast Ohio, but anyways, that's what we're going to do. The wind speed is 2.7 meters per second. We know the humidity, and we've got a pan surrounded by 100 meters of dry fallow. Dry fallow means it's a field that isn't currently in production. It's an agricultural area, but nothing's planted and growing. It's measuring 4.2 millimeters of evaporation per day. And so the first thing that we're given is the pan evaporation. E sub P is 4.2 millimeters per day. And we want to know what's the monthly reference evapotranspiration for short irrigated grass turf. And then the other thing we're going to try and find out is how much irrigation should farmers provide in order to overcome this evaporation that's occurring. All right, so the weather parameters we have is relative humidity, 65%, and it's surrounded by 100 meters of dry fallow, 100 meters dry fallow, and then wind speed is 2.7 meters per second. Okay, let's go back to the last table and take a look at what kind of a pan coefficient we're going to see for that. Okay, so we can consider the dry fallow as dry bare earth. It's not a short green crop, and so we're going to use a pan coefficient for case B. The relative humidity of 65% puts us in this column. The wind speed of 2.7 meters per second puts us in moderate wind, and so we're in the medium moderate wind, and then it has 100 meters on all sides. And so that means regardless of what direction the wind is blowing in, here's our pan, and it's 100 meters to the edge of the field. And so that means our pan coefficient is going to be 0.60. So K sub P is 0.60. So what that means is that the actual evaporation from the soil and from the ground, the E sub T, is Kp times Ep. That means that only 60% of the evaporation that we see from the pan is going to be occurring in the field itself. And so if we see 4.2 millimeters per day from the pan, then the evaporation from the field, let me get my calculator going. (2.52 millimeters per day. So let's think about this logically. Why would there be more evaporation from the pan than there is from the soil? Okay, so the grass is shielding some of the soil, that's right, and whereas the pan is just open, free water. And so it's always going to be easier for water to go from the liquid phase to the vapor phase just when it's a free surface of water than if the water is inside of a grass. It is going to have to travel through the grass. It's going to have to go through the cell membrane of the grass to be exhaled into the environment. The soil, like we said, is partly shaded. The other thing about it is that the soil isn't 100% water. So there might be some moisture 1 inch down into the soil, but it has to travel up through the soil to get to the surface. And so you'll notice none of these pan coefficients are greater than 1. It's never going to be the case that it actually has more evaporation from the soil and the trees and the plants than you observe from the pan. The pan is always going to be the upper limit of how much theoretical evaporation there could be. But in this case, we're estimating that the Earth is going to be, the Earth and the plants are going to be losing 2.52 millimeters per day. And so on a monthly basis, which is what this problem asks about, what's the monthly reference evapotranspiration for a short irrigated grass turf? So if we multiply this by 30, 75.6 millimeters per day is how much evaporation that we're going to observe. Month. Thank you. Yes. Now, let's look at the difference between, since it's surrounded by dry, bare area, and if it's surrounded by a short green crop. So we used a pan coefficient of 0.6, but if it had been surrounded by grass, then it would be 0.75. So what that means is if we're planning to put grass there instead of, this is how much evaporation from dry, bare area. How much evaporation would there be if it was grass? there's actually going to be more evaporation if it's grass. We notice that the pan coefficient is 0.75 instead of 0.6. And so we need to scale it up. And so 75.6 millimeters per month. And then we multiply that by the ratio is 0.75 to 0.60, because this is the pan coefficient for the dry, bare earth. This is the coefficient for grass, essentially, for a short green crop. So that means that if we put grass there instead of the fallow crop that's there now, then we would need to account for 94.5 millimeters per month. So now this assumes a lot of things, though. Okay, so this is assuming that it stays all the time 2.7 meters per second. That's a pretty heavy wind. It's not always that windy. And the other thing is it's assuming 65% humidity. That's maybe a little bit on the high side depending on the season. So we could expect it to vary quite a lot. And you got a sense for that in the homework that you did, where you were taking 1 day of solar radiation data, and then I asked you to project from that 1 day over to a whole month. Well, not every day is identical. And so when you projected your 1 day over a whole month, I think you got something in the range of 4 inches per month of evapotranspiration. Is that right? But then the other source of data said something closer to 11.5 or 12. And so one of the reasons for the discrepancy there is that you can't take 1 day of data and say the whole month is going to be like that. So where we're doing that here, where we're saying we maybe need to have 94.5 millimeters per month of water to keep grass alive, that's just a ballpark estimate, because some days are going to be more windy and less humidity, which means you'll have more water that needs to be added. Other days there will be no wind, it'll be very humid and maybe cloudy, and so there would hardly be any evapotranspiration at all. But it's good for an estimate anyway. It's better than nothing. Why is it closer to the pan, why is the pan coefficient higher? I think it's about moisture availability, that in a short green crop, there's just more water to evaporate. Like what's limiting evaporation in dry, bare earth is the fact that there isn't as much moisture trapped in the soil as there would be in a crop that's green and has roots going down under the soil and can kind of draw the moisture upward. It's about moisture availability. Okay, so that concludes our discussion of evaporation. Now we're going to talk about infiltration. And we're going to start by asking, how do soil properties influence the behavior of water? So there's three basic things in hydrology. In the modeling of hydrology, there's lots of little things, but if we're going to just be very broad about it, we'd say, here's the ground surface, and from the cloud there's precipitation, big drops of water. All right, so it's coming down, and it can either infiltrate or run off. And so this is precip. Sometimes runoff is also called rainfall excess. It's called rainfall excess because it means the rainfall that is in excess of the amount that's going to infiltrate and in excess of the amount that is going to be consumed by wetting the surface or evaporation. You know, surface wetting and evaporation, those are kind of minor losses or minor abstractions when it comes to trying to estimate the runoff. But infiltration, I spelled that wrong, by the way. That's better. Okay, so what we're going to be talking about now is how much water makes it underground during a storm event. And to be able to estimate that, you know, if we fast forward through all the theory, at the end of the theory, there are two models that I'm going to teach you, two different like equations or methods that are used to predict how much water gets underground when it starts to rain. And those models look at the soil type and they look at how hard it's raining. You know, those are the factors you maybe would expect are going to have an influence on how much infiltration there is. But before we get to that end point of just some empirical model, it's important to understand the theory that goes into the empirical model, because both of these empirical models have shortcomings. They're not perfect estimations of how much rain is going to get under the soil. So let's talk about the actual physical phenomenon that help govern how much water makes it underground. One thing to look at is the difference between clay and sand particles, because those are at opposite ends of the soil map. I guess maybe gravel is even further than sand, but if you look at how tightly bound water is to different types of soil, water is always going to be most tightly bound to clay. And the reason for that is that clay particles are very, very small and they have a high surface area. And since they have a high surface area, and because of their small size, the clay particles actually have a charge to them. They have a negative charge. These small, thin layers of clay basically have a negative charge all around them, and the water is attracted to that negative charge. And their high surface area also means that water, in essence, maybe the crude way to think about it is it's hard for water to make its way through these voids because they're so small. And because there's so much surface area, the water is trying to seep around a very high area before it makes its way through a thick column of soil. Sand, on the other hand, you can see that there's a variety of different particle sizes. Like here's a big piece of sand. This is maybe 2 millimeters in diameter. If we picked up a handful of beach sand, some of the grains would be large, some of the grains would be very, very small. And what happens with that is that the small grains pack in between the voids of the large grains. But still, there are these voids here. Some of the voids are large, some of the voids are medium, and some of the voids are very, very small. Like look at this gap here. It's a very small gap. And in fact, that small gap is almost like when we were talking in fluid mechanics about surface tension. If we have a tank of water and we put in a glass tube, you'll remember that the water will rise up in a glass tube because of surface tension, because the water wants to be in contact with the glass tube. It'll rise up a little bit naturally. But if we have a small diameter tube, very small diameter, then the water level will rise much higher because the surface tension forces that are pulling the water up in the glass tube are greater than the weight of the water that's above the water line inside the glass tube. So this was called surface tension. And the same thing is happening here, that when there is a big opening like this, the water can pass through that opening very easily. But a small opening like this, the water once again has forces that's binding it to the surface of the grain. The water wants to coat the grain before it's able to pass through that void. And so where there's very small voids, there's a high level of attraction between the water and the space that it's flowing through. And that actually can suck the water up from the water table. We'll look at some diagrams of that today, but you know, this is the starting point of talking about how water and soil interact with each other. And a big part of it has to do with the size of the voids and the distribution of voids. This is a really important word, distribution. Remember, we already talked about spatial distribution. And spatial distribution was talking about how things vary over space. Maybe it rains a lot in West Virginia, but it rains very little in Texas. You know, that's spatial distribution of precipitation. We talked about temporal distribution, how there is, at the beginning of a storm, very little rainfall, but suddenly the rainfall intensity gets high and then it starts tapering off again. So we had time and we had amount of precipitation. So this was a figure that illustrated temporal distribution. So inside here, there's also a distribution. It's a void size distribution. And so if we were going to take a look at this, then we would have relative amount, and then we have void size. We have small, and we have large, and it would maybe be normally distributed. So what this figure says is that if you look at the soil, there's only a few of these voids that are really big, not very many of them. So there's some of the soil has a large void size, and there's only, what did I do? There's only a few cases, look at, there's maybe 1, 2, 3, 4, only a few cases where the void size is really small. The majority of the time, it's a medium-sized void. So it's not all the same size void. So there's a distribution, there's a whole spectrum of different void sizes there. And that's going to be important when we talk about soil moisture. Okay? This is a figure that maybe you've seen before in soil mechanics class. And the only point that I want to make when we look at this is that soil is a mixture of components. And we don't want to be naive and say that we have soil that is sand. Because it's only in a few places. It's pretty uncommon that a soil would literally only be sand. I mean, more commonly, soils will be a mix of partly clay, partly silt, partly sand, and then on top of that there may be gravel as well, or rock underneath it, or sections of the soil where there are rocks inside of it. And so there's a whole range of possibilities of different percentages of clay, silt, and sand, and even if we have a large field and we dig down and we take a sample at one location, it may be some percentage of each of these. But then what we call sand is also itself going to have a variety of sand grain sizes. Back to this figure, even though this is 100% sand, the sand grains are varying in size. And so soil is very complex in terms of what it's made out of, the variety of sizes, and then also the spatial distribution. Within a watershed, it may be like a clay silt on one end of a watershed, and it may be more sandy on the other end of a watershed. The next point I wanted to take a look at is some different properties and how those vary for sands on the one end of the spectrum, and then on the other end of the spectrum is clay. And remember, what distinguishes them is how tightly bound water is to clay versus sand. Water has a much more difficult time passing through clay. Clay holds on to the water compared to the sand, which the water is able to drain through more easily. And so porosity, this first property, there's a range of typical values. And so the reason why there's two curves and they both go with porosity, one is that upper limit for typical porosity and one is the lower limit for typical porosity. And so the interesting thing it's counterintuitive is that I tell you soil holds on to the water, and so maybe you'd think that that means there's fewer voids. But actually clay has more voids than sand does. So porosity is talking about the pore space relative to the total volume. If we go back to this figure, porosity is saying how much is there empty space compared to the total area altogether. And so if I drew a unit volume, porosity is going to be a measurement of how much empty area there is inside of that unit volume. So if I draw a cube, and now I'm going to measure inside of here how much is solid, how much are the spaces relative to the total volume. That's porosity. It turns out that the soil that is sandy has a lower porosity than the clay. If you look at this diagram of clay, it looks like it's mostly empty space. And the properties that are illustrated here bear that out, that the typical clay porosity is going to be in the range of 45 to 50%, whereas sandy soils would have porosity just over 30% up to about 45%. So that's kind of counterintuitive, and so what you need to learn from that is that clay's affinity for water isn't because of it having less porosity, but it's because of the negative charge of clay surface. It's the negative electrostatic charge that's associated with the high surface area of clay. Field capacity is another interesting property, and what it means is, let's say that it rains and you allow the soil to drain just by gravity. So you're having the soil drip dry so that all of the excess moisture that can easily drain out of a soil can. And so it's a measurement of how much moisture is remaining in a soil after it has drained. And you'll notice that the field capacity is much higher for clay than it is for sand. And so that's right along with what I've already told you, is that the clay holds on to the moisture more easily than the sand does. The water passes through the sand very easily, and so its field capacity a couple of days after precipitation may only be 0.1. And so what that means is if you compare the voids to the field capacity, that tells you how many of the voids are saturated. And then the other thing is the wilting point. The wilting point looks at how easily plants can take the moisture out of soil. And so what it's showing is that the plants, they can still take water out of sand when the moisture content is as low as 5%. But it's much more difficult for plants to take moisture out of clay. Clay has to be more wet or else the plants will begin to die, is the interpretation of this line going up. The reason why the wilting point is higher for clay is that the clay is holding on to the water. The clay won't allow the plant roots to withdraw the water as easily as silts and sands. In the case of sands, then the plants can continue to withdraw the water even when the moisture content's very low. So the main interpretation of all three of these is just moisture moves through sand more easily than it does through clay. There's an interesting way of measuring how much the soil is holding on to moisture. There's a measure of the suction or the tension in the unsaturated zone, and let me define for you what the unsaturated zone is referring to. Here I previously drew the ground surface, and we know that water is going down into the soil when it rains. Below all of this, if you go deep enough, there's rock. Okay, and it's sort of like the water table is perched on top of rock. And so if you go up to here, here is the water table. And you can think of that, if you dig a hole, how far you have to dig before the water starts to fill the hole. That's what the water table is. And so the voids are saturated with water. And above this water table, the voids are unsaturated. Does unsaturated mean dry? Are the voids totally devoid of water? Would it be right for me to say, here it's wet, here the soil is wet, and here the soil is dry? No, that's not accurate. That's oversimplifying the situation. Because even above the water table, there's still moisture in the soil. It's just that below this level, all of the voids are completely full. Above this level, some of the voids have water in them. Those small little voids, they have water above the water table because of the capillary effect. And there's probably moisture close to the surface because remember during infiltration the water is moving through. So we have different names for this zone. So it's below the ground but above the water table. We call this, I'm going to write the names here, it's the saturated zone, unsaturated zone. Sometimes it's called the vadose zone. And whenever I hear vadose zone, I think of Darth Vader. So I don't know. Usually the phrase the vadose zone, that's used when it's talking about environmental issues, like if there's a gasoline spill. They call this the vadose zone. And if gasoline spills in here, then in the vadose zone, they can actually take fans and they can blow air through the vadose zone to try and air out the gasoline. But if the water gets down under the water table, then they have to pump it out, like with liquid pumps. So the vadose zone is also sometimes called the zone of aeration. So 3 names that mean the same thing. It means that there's some air and some water in the voids. And the void is just the space between soil particles. Okay, so we're talking about the unsaturated zone. This slide is talking about how much suction is there or tension in the unsaturated zone. Tension is a measure of how badly the soil wants moisture. And so remember the capillary effect, that a small diameter tube will draw water up from the water surface higher than a large diameter tube. So the soil void is basically just like a tube. You can think of it, if you think in 3-dimension of a lot of small diameter soil voids, it's like a glass tube essentially. And so there is this device where the tensionometer, as it's called, you jam it down into the soil carefully so that you don't disturb the soil. You jam it. You jam it carefully, and then there is moisture inside of this tube, and actually the soil will start drawing the moisture down out of the tube, but it creates a vacuum above it. And so before you put it into the soil, initially the water level was all the way to the top. But then the soil is going to try and suck out the water from this, maybe it's a straw, you can think of it like it's a straw that's full of water. The soil is trying to pull it down, but it can't pull it all of the soil out. The soil can't pull all of the water out because there's nothing to replace what is in this vacuum area. And the gauge on top is just measuring how much of the water is evacuated from the tube and how much tension is there from the soil trying to withdraw it. And so this gives you an idea, this kind of a test gives you an idea of how the soil is going to behave when rain occurs. And the higher the tension, the faster the infiltration will be. So a test like this is showing for a couple of different soils the tension compared to the saturation. Saturation, again, is talking about how many of the voids are empty and how many of the voids are already full of water. So my question for you is, what's the trend here? When the soil is more saturated, what happens to the suction of the soil? So the suction is less. So what does that mean as far as rain? Think about when a rainfall event, when the rain just barely begins, there's more infiltration at the beginning of a rainstorm because the soil is going to be sucking the water down. The soil is more hungry for moisture. And it's not the soil has a brain and the soil is feeling hungry. It's just that there is more tension because the voids are empty. But as the saturation increases, if there's the rainstorm, then the voids are filling up, then the driving force is going away. There isn't as much of a force pulling the water down. So it's actually, sometimes we think that what's getting the water into the ground is there's a pool of water, you know, it's sort of like a pond. and that's what forces the water down, and that can, but that's not all of it. The water is actually getting sucked into the soil by the soil. But during the rainstorm, as those soil voids increase, as the saturation goes up over time, then the suction decreases. And we'll see that when we look at some diagrams of infiltration over time. The zone of saturation. Thank you. Good question. Zone of saturation. Or the Luke Skywalker zone. Just kidding. All right. So let's look at water movement in the unsaturated zone. When it rains, some of the moisture is going to evaporate. And here it's showing that exfiltration. Exfiltration is the opposite of infiltration, and that's evaporation from the soil is considered exfiltration. So as the water is infiltrating, it can move down, but also water can move up from the saturated zone. Here it's talking about capillary rise, and so there's some moisture that's going up from the groundwater table. Recharge is what we call it when infiltration is increasing the depth of the saturated zone. And any water that isn't taken up by plants or moving sideways through the soil, anything that actually doesn't make it underground is what's going to be the overland flow, the runoff. It's going to be the rainfall excess, or overland flow is what isn't infiltrating. And so that's why we're so interested in infiltration, is just because ultimately we want to say how big that culvert has to be or how deep the water will be in a stream. I'm showing a video to my fluid mechanics class today, and I want to show it to you right now. I just remembered it. It's not having to do with infiltration, but it definitely has to do with hydrology, and I don't want to forget showing it to you, so I'm going to just stop right where I'm at and indulge my scatterbrain so that I can show you a YouTube video, because these cats are just so cute, I can't stand it. All right, let's see if I can find it. Aren't you glad you're not taking fluid mechanics this semester? Almost there. Oh, shot too far. Here it is. Oh, I forgot how slow this laptop is. All right. It's loading.
Where'd she get?
Just right here to the left. High ground!
To a certain time.
You got it, Mike? Yeah, I'm gonna film it.
All right, so these guys are out hiking, and you can see it's not raining around them. Here's a dry creek bed, dry-ish. Here's a pond, a little puddle.
Oh, there it is.
They hear a roaring in the distance. They know something's happening. And here comes a flash flood. It was raining in the watershed.
Whoa, it's coming
maybe
quick.
20 or 30 miles away.
Awesome. Should I probably get out of the
It
way?
seems like it's maybe not dangerous at all. Just a small stream that's coming through. They know about it. This guy, he's seen it.
Dang, that's bigger than the
Porosity's
last.
moving up onto the sides. You can see it's pushing
Wow, it's bigger than the last.
So that's serious, right? I mean, this is no screwing around. Never camping. Never camping in a creek. Because by the time you wake up, it's all over.
We know what to look for. That's crazy. It hasn't even been raining. That is so deep.
Sweep you downstream.
Yeah.
So this is why we are studying infiltration, is because in rugged canyons like this rock is not infiltrated.
Sense to get out of the way.
Even though the soil is dry, this creek bed was dry before the event started, the water is arriving so fast that it's immediately exceeding the infiltration capacity. The reason why there's runoff is because the precipitation rate is so much larger than the infiltration rate. Good video, right? Yeah. Okay, back to soil water. Equally important, less dramatic. Okay, so we talked about field capacity, wilting point. One of the things we haven't mentioned so far is hygroscopic water. And what that is that's the water that's around the edge in the voids, and it's very tightly held. It is the water that's just forming a small membrane in the soil voids. So remember, we have soil grains, like here is sand, and it's touching at different sand sizes. All right, so there is some water, but the only way you can get the water out is by putting the soil in the oven. There's that small, thin layer of water that's covering the outside of the soil, and that's the hygroscopic water. The plants don't have enough suction in the roots to get that water off of the soil. And this hygroscopic water is tied to the diagram that we were looking at before of the wilting point, where the wilting point for clay is very high because there's more hygroscopic water. It's the water that's used to wet the surface. There has to be a lot of that water available wetting the surface of the clay before there's anything left over for the plants to remove. But in the case of sand, it needs less water to wet the surface because there's less surface area, less specific surface area in the case of sand than for clay. All right, here is a soil profile. We need to get in the habit of looking at cross sections of the subsurface and being able to interpret what we're looking at. And so here's the rock layer at the very bottom. Impermeable layer means that there's rock, or in some cases a really impervious compacted clay that we say the water table is perched on top of. So above the impermeable layer, here's the saturated zone. And you'll notice that it's saying that the water content is equal to the void ratio. And so all of the voids are full when the amount of water that's in the soil is absolutely equal to how much space there is. That is the very definition of saturated zone. Now, above the saturated zone, they call this the capillary fringe. And the water content is elevated in that zone because this is the zone that actually the soil is able to suck water up from the zone of saturation. Now, there's going to be some large voids where there isn't enough tension to fill the large voids entirely. But here in the capillary fringe, the water content is above normal because of the surface tension effect of water and the attraction that the water has for the small pores. So The reason why the water level is elevated in this zone is because the small pores are still full of water. Down here, all of the pores are full of water. Above this line, the large voids aren't saturated, but the small voids are still saturated because of capillary fringe. And then in this intermediate zone, that's between the capillary fringe and here in the root zone, that's essentially how deeply you can go and plants are interacting with the water in the soil. And so there might be in the root zone less moisture in the soil because the plants are removing it. But there again, it depends on how soon after a storm we're looking at this profile, because immediately after a storm, it might be that the root zone is more saturated than the intermediate zone because it's closer to the location where the recharge was occurring. And so we have to be aware of both the spatial distribution of moisture in the subsurface, meaning, vertically, how does the moisture content vary? Down here, there's lots of moisture. Up here, they may be less moisture. But then also the temporal distribution is where in the storm are we? Is it before a storm, after, during a storm? And we're going to look at profile maps of actually how a wave of water goes down through the soil as it rains. And we just looked at a wave of water going through a creek bed. We can also look at a wave of water infiltrating down through the soil. Yeah. So this means the water content, theta, and then this is the void ratio. So they're saying the water content is equal to the void space. So all of the voids are full of water in the saturated zone. This diagram of infiltration is making the point that the water travels side to side in addition to going straight down. It also moves away in the downstream of the gradient. So that if infiltration happens in one place, here you can see it was raining only over here, the water table becomes elevated, and because the water table is higher here than it is there, and on the right side of the screen, the water table is only as high as this is a river or a pond. So the water table is going to match the elevation of this pond or river. And so there's sideways movement of the groundwater because of the gradient in the water table. So when we try and classify the rate of infiltration, we're going to look at what condition the soil surface is in. Like if it has been disturbed, like scraped with a bulldozer or compacted by people walking on the soil, then infiltration will be decreased. How much vegetative cover there is. Vegetative cover helps infiltration. You've probably noticed if you walk from here to Gullickson Hall, so on the sidewalk on the other side of the street, the grass on the left side of the road doesn't look very good, right? Like that grass is in bad shape because the athletic department is always driving their little buggies and people are sometimes walking on the grass. And so it's kind of dirt, a little bit of grass, and the dirt is really slick because it's been stepped on so many times, it's been compacted. So there would be very poor infiltration on that little median strip of grass between the sidewalk and the road because there's not much vegetative cover and the condition of the soil surface is poor. And the other thing that we have to look at is the numerical properties that we can classify for the soil, like porosity, conductivity, moisture content, and so on. All right. This is a complicated diagram, and we're going to spend a couple of minutes looking at this because it's the sort of diagram that's important for you to be able to explain. You need to be able to tell a story from the diagram. And so what story is this telling? At 0 is when the storm begins. And so it's saying along the x-axis are different periods of time. Now, on the vertical axis, It's the rate relative to the precipitation rate. So the precipitation rate we'll assume is constant. During a storm, it's raining a certain amount. But what these are, all of these rates are how quickly moisture is going in other places. And so the infiltration rate, which we've been talking about infiltration rate starts high, and then infiltration rate is decreasing as the storm goes on, and then finally it reaches a plateau. Like it sort of reaches a constant rate. We looked at a diagram a few slides ago that explains this phenomenon. Why is it that infiltration rate begins high but then decreases? That's right. The soil suction or the soil tension decreases as it gets filled up. And so infiltration rate is high at the beginning because the soil is wanting the moisture, but then as it gets more moisture, that driving force that is drawing the water down underground decreases. And so as infiltration goes down, the water has to go somewhere else. And in this diagram, what they're showing is that the infiltration rate never was as high as the precipitation rate. You know, if precipitation rate is 100%, if it was initially raining 1 inch per hour, it looks like the infiltration rate at the beginning at best was only maybe around 20%. So where did the rest of the water go if it's not going underground? Well, one of the first things that happens is it fills up surface storage. So surface storage is going to be things like puddles at the surface or wetting the surface of the ground, like getting the concrete wet before the water is moving over the surface of the concrete. Water will be moving through the soil moisture. So in the zone of aeration, the moisture is going to increase. Although it's not going to become fully saturated yet, it takes a little bit more time before the water gets down into the saturated zone and there can be groundwater flow. And once there's groundwater flow, meaning that the saturated zone is high in one place and lower in another spot, like it's not level anymore, so the water is moving side to side, then actually the water will move sideways through the unsaturated zone as well. And then lastly, you can see overland flow. That's sort of like a shallow sheet of water flowing over the surface. And eventually, when there's enough overland flow, then finally there will be channel flow. So that's the last thing during a storm, is that all of the infiltration that can occur and all of the soil moisture that could increase has happened, and there's still leftover water, then finally channel flow will occur. The slide makes the differentiation between detention and retention. And remember, when we were talking about ponds, we talked about how detain means just to temporarily slow down, and to retain means to keep. So here retention is holding onto water for a long period of time on a relative basis, whereas detention is kept only for a short period of time. And so it's depleted by outflow, where the water is just moving away from it, but retention is removed by evaporation over the long term. So this figure tells a story, and I hope that you'll be able to tell the same story. Okay, again, the zone of saturation is below the water table. The zone of aeration is above it. Within this zone of aeration, there's the capillary zone, which is immediately above the water table, the intermediate, which is in the middle, and then the root zone, or also called the soil water zone, is where vegetation is found, and that's where the depth of roots can extend. So this is a diagram that's showing those three different zones relative to the zone of saturation. Below them all is the impervious formation of rocks. All right. Here's another device, sort of like the tensionometer, a kind of an ingenious way of being able to experimentally determine the water's capacity for infiltration. And this is called a single ring infiltrometer. And I know this looks like it's a pan, but it's not a pan. At the bottom, it's open. So it's just only a ring. And at the bottom, it's open so that you can set it down into the soil gently. You don't want to jam it in and pack the soil and disturb it. So they gently will set this down into the soil and maybe get it to overlap with the soil, embed it maybe a centimeter or two. But then what happens is you can do two different tests. You can constantly pour in more water, and so you're trying to keep the depth the same, and then just by how much water you're pouring in, then you can determine how quickly the infiltration is occurring. And this cross-sectional view shows that, at time 1, the water has infiltrated outward and downward. At time 2, it's getting deeper and wider and so on. So there's a constant head infiltration test, or there can be a falling head infiltration test. And in the falling head test, you don't keep pouring water in. In the falling head test, you'd use some sort of a gauge to measure how quickly the water level is declining. So that's the easiest thing to do, is a single ring falling head infiltration test. A little bit more sophisticated is if you want to try and avoid this sideways movement, because the purpose of this test is to try and estimate what happens when it rains. And this isn't a good estimation of what happens when it rains, because it's over such a small area. Usually when it rains, it's not only going to rain on 12 inches of soil. It would rain for miles in both directions during a storm. And so this is a poor approximation. And one way to overcome that is with a double ring infiltrometer. And in the double ring infiltrometer, this diagram is showing that the outer ring, the purpose of this outer ring is to satisfy all of the lateral movement of the water, because in this single ring, some of the water is going down, but some of it is also going outward. And we don't want that outward migration of the water. We only want to know how much of it is going downward. We prefer to classify just the two-dimensional flow of water. And so this will do that. The double ring infiltrometer will, the water in the outer ring goes sideways and down also, but then the water in the inner ring is able to flow only straight downward, because the sacrificial water that was in the outer ring is already quenching the thirst of the soil adjacent to the water that's coming down through the single the single inner ring. So again, you can also do a constant head or a falling head test, but this is a little bit more sophisticated because it provides for one-dimensional flow. So this is just a way of testing the soil and finding out how quickly water will infiltrate into it. And then, as you might expect, there are tests to extrapolate the behavior of this to the behavior during a rainstorm. Just like the evaporation pan. Remember, there's the evaporation pan. We use that to extrapolate to how evaporation will actually occur for a crop. Here, this isn't a real rainstorm. This is just a test that we can then empirically correlate how it behaved for the infiltrometer to how it behaves when actual raindrops are falling onto the soil. Some of the differences, if you think about a storm compared to this depth, during a storm there won't instantly from the very beginning be 6 inches of water on top of the soil. That's not realistic, that there would be instant ponding. Also, during a storm, the raindrops hitting the earth actually drive some of the water down into the soil, because the raindrops have achieved terminal velocity, and they're going, depending on the size of the raindrop, 30, 40, 80 miles an hour when the raindrop goes down. And it doesn't hurt your skin, but it can push aside the soil grains enough to help increase the infiltration rate. So some of those things are not accounted for by the infiltrometer test. Here's the profile of the water content underground. And this is showing the capillary effect. Moisture content, you can see at the water table, is saturated. And this theta naught is the minimum water content, that if you drain the soil, there's still going to be some moisture there just to wet the outer surface of the soil grains. That's the minimum moisture content. And so as you go up from the water table, the moisture content is decreasing, and this is the capillary zone in here. And we've already talked about the capillary effect, and that the fact that surface tension raises and lifts the water up off of the water table. And here is the definition of porosity. It's again that diagram where we're looking at how many of the space, how much of the space inside of a certain unit volume is empty and filled with air versus how much water is there and the solid particles that are present. And the typical porosity would go between about 25% to 40% of the total volume of soil. Here's the definition of moisture content. It's the volume of water relative to the total volume, including the soil grains and the voids. And the highest that the moisture content can go is moisture content can't go any higher than porosity. There can't be more moisture than there is space for the moisture. And during a storm, the moisture content goes up to saturation as a maximum. So the change in moisture content, when we do problems like this in the homework that I just handed out to you earlier at the beginning of class, delta theta means the increase in moisture content that occurs during a storm. And then after draining, the residual moisture content, theta r, is how much moisture is kept by the soil to keep the soil grains wet. So here's one more definition here, effective saturation. So in effective saturation, you're having to look at how many voids are actually available for holding on to water and how much the water content can increase during a storm. So theta sub r is the minimum amount of water that will be in the soil after it's drained. And theta is whatever water content that you've got. And this is the difference between the porosity and the residual moisture content is the effective porosity, or how much water a soil can hold on to. And so at any particular time, the effective saturation is a little bit like relative humidity. There's an analogy there between, relative humidity is classifying how much water the air can hold on to. The effective saturation is saying, compared to how much water content can be in soil, how much is there right now? All right, that's the last slide, right? Do we keep going? Oh, okay, Darcy's. All right, I wasn't sure which slide I stopped with. All right, Darcy's law you probably remember from soil mechanics, and it's a way of classifying the hydraulic conductivity of soil. We've talked about how clay is bound to water more tightly because of its negative charge on the soil surface. And sand, on the other hand, allows for water to pass through it more easily. Darcy's law is a way of testing that to find out what is the hydraulic conductivity of soil. So here is the test apparatus that's showing it's like a pipe. You can think of it as a cylindrical pipe that's crammed full of soil of some sort. Here it's sand. We would want to know the cross-sectional area of that pipe. And so if it's a circular pipe, it would be pi d squared divided by 4. The flow rate of water down through the soil is going to be measured using these pools here. They're these two different pools that's on the head end and the bottom end of the device, I think make a lot more sense if we show this device oriented sideways. I mean, this is the classic way of showing Darcy's law, but let me redraw it in a way that makes more sense to me. So here we've got our, think of it as like a big PVC, a plastic pipe that's full of soil, but we connect it to a reservoir, and here is the water. It's flowing this way, and then it's connected to a reservoir over here. The water level's not as high. So there's a difference in elevation here. And Darcy's law says that if you find the difference, delta H is H1 minus H2, if you find the difference in head on either end, and you measure the length of the soil column, and you know the cross-sectional area, and then you measure the flow rate Q, how quickly is water moving from this upper reservoir to the lower reservoir, there's some parameter K that varies depending on what the soil is. And if there is clay inside of this tube, water is going to move very slowly from the upper reservoir to the lower reservoir. If it's gravel, then the water moves very easily between the two reservoirs. And so this parameter K, the hydraulic conductivity, tells us how easily water can move through the soil. And that's what Darcy's law gives us, is an expression that relates this soil property to the flow rate of water through a soil. So in the case of infiltration, if you want lots of infiltration, then you want a soil with a high hydraulic conductivity, because it doesn't require much of a head differential to allow large quantities of water to move through it. Sometimes Darcy's law is simplified by the head differential H2 minus H1 divided by L is called J. That's just the, you can think of that as the slope of the water surface. And lowercase q is a flux. It's a flow per unit area. So they call that Darcy flux. But I don't know why visualizing it oriented sideways makes so much more sense to me. I guess when I see it oriented vertically like this, I start thinking about, well, is it gravity that's driving the water through the soil? And it's not gravity. It's the difference in the water elevations that's driving water through the soil. It's the difference in the heads. But the test apparatus itself is actually vertically oriented in most cases.
Is the flow rate not the same?
Yeah. Yes, it is.
It is the same.
Yes. Because inside the column, it's saturated. So the flow rate is the same. Yeah. Yeah. Yep. This is more a Huffman thing than a weight thing. I walk on eggshells when I start talking about soil, because I got a B- in soil mechanics when I took it. I wasn't the strongest student in soils. It was my worst grade in college. Well, besides a 6 a.m. PE class that I constantly forgot to wake up for. All right. So we don't have time for this Darcy example. We'll pick back up on Thursday. Take a look at the homework. I don't know that you'll be able to solve it quite yet, but if you take a look at the homework and just start thinking about it, then that'll make our lecture on Thursday, wait, today's Thursday, next Tuesday, more meaningful. I hope you have a great weekend. I will see you on Tuesday.